This is just a short video on how the recommender systems work. Recommender systems are quite important. If you go to Netflix, Netflix will give you recommendations based on perhaps the other movies you might enjoy. Or if you go to Amazon, it might recommend products based on what you have bought in the past. So the question is, how do we do that? And how do we build such a system? So even Google has recommender systems. When you search for an item, the Google will show you all the related uh, ads related to that item. So some of the best big issues of recommender systems designing is the lack of data. You need to have a lot of data to know what to recommend. Also, changing data is a problem because if data changes quite a bit, then we have to deal with that. Changing user preferences. Users might change their preferences from time to time. So you couldn't have a recommender system that is static. And there could be unpredictable items. There's no data to predict these items. And so the idea would be that what are some of the issues with recommender systems? All of these. So let's go to concept of recommender systems. So there are content-based systems. That means your input is either user and item metadata, such as you will know user gender, item publication date, but they are independently maintained. In collaborative filtering systems, we have more information about what users like which items. For example, where they click and number of stars they give, those things are available to us. So what information can be used to make predictions? We can definitely make user information to do predictions. If you know something about user preferences, you might be able to do that, such as age, location, profession. So you might do target advertising on those users. Item information, if you have the budget, actors, release, and you might be able to implicitly sort of tie the users and items together. Or you can have explicit information such as use item information. So in this case, we're going to recommend items that are most similar to what I have bought before. So in this case, we only consider what I did. And then based on that, we're going to predict similar items. So, or you could say recommend items that I may not have bought, but they are bought by other users who are most similar to me. We have to define what similar means. So recommender system can fall into some sort of supervised learning. We know some output, for example, which items the users have purchased. And then so we can train a classifier on that. Or unsupervised learning, because we can find structure among similar items, or we can find structure among similar people. So challenges in building recommender systems are the lack of user ratings. Users only provide very limited data. We only have the data that the users give us, but doesn't know what they think of the other items. We can combine personalization and generic items that you may like, items under 25 or in a group gardening, and so on. There are also privacy concerns that you have to deal with. So I will just skip through this one. This is a very famous Netflix thing. We don't need to discuss it in the video. So basically, your files can come in this form. You may have user rating files, so which users have rated which movies. And then we know the movie ID and the title and the genre. So if you merge these two data sets, you might be able to get a lot of things. This is the rating matrix, which is typically very sparse. So the full data is very large, 26 million ratings, and so on. So we're just gonna, a small data set can be like 100,000 ratings. So in this video, I think my focus would be on collaborative filtering. In other words, recommender systems that makes recommendations based solely upon preferences that other users have made for those items, such as X bought Y, so and Y is a friend of Z, maybe X will buy Z. So here's how the user rating matrix may look like. Users are the rows and the ratings are the columns. So ratings are the movies. And so each movie is rated by this user has rated 2 movies and so on. As you can see, this is going to be a very highly sparse matrix because there are a lot of information is missing because this user hasn't rated this movie or that movie. So now the challenge is to fill in the missing entries. So how do we do that? For example, if you take these two records and how do we fill in this entry or this entry based on what the user preferences are? So what are possible approaches to collaborative filtering? So we have user-user approach. We take users' similarity to decide what the missing item is. So we find the uses that are most similar to me, items rated by both of us, and then predict the scores for the other items based on the average. Item-item approach is essentially we're going to find items that are most similar to a given item based on all the users who rated both items, then predict the scores for other users based on the average. In other words, we are just going to look at the rows where the users are or columns where the items are to come up with some kind of an estimation. There's also other methods such as matrix factorization, which is finding a low-rank decomposition of the X matrix that agree at the observed value. So let's go into a simple idea here. Suppose we like to do user-user and item-item approaches. So the basic idea is find other users who are similar to me. How? We can find the correlation coefficient or cosine similarity. Cosine is similarity gives you given two vectors, two users who have vectors of ratings. We want to find the distance, cosine distance between the two, or the angle between these two vectors. Or we find the correlation between these two things, which is also can be done. So how to find the correlation coefficients? Find items ranked by both users. We want both users' items ranks and consider rows of the user matrix item. Same process as with columns for item-item ranking. So here's the user-user approach hypothesis. Hypothesis is we are trying to find parameter theta to rate user I and the item j. So a prediction problem can be defined by a formula like this. The ij entry is missing, so x hat ij is the estimation that I'm going to make for the ijth entry. So I'm going to say xij entry, I can either take the average of the ith user's ratings and then find all the other users k, where the kj, the jth element, we're looking for the kth column, jth column, where xkg is not 0, and then find some weight, and then we will talk about how to find this weight, and then find the how far this user k is from its own mean, which is x bar k. So we find all these users k's who are closer to the user I. And then we can limit this to few k's if you like. So x bar I means the user I ratings, and wik is some kind of a similarity function between users I and k. It could be the distance or the cosine relation or cosine angle, or it could be the Pearson correlation. So we can restrict some to only the k users most similar. Here we find the difference between the other user and the mean. And if there are no similar users to I, obviously, in other words, if you cannot find k, any k where it's similar to I, then you can make the wik 0. So this would be just the average. The prediction for the ith rate jth column would be, jth item would be the average, which is not a good one, right? Okay. And the reason we want to do this sort of a difference is that people have similar ranges in relative rating. So we take the difference between how far all these k uses from the mean of their own mean, and then we multiply by this factor. So let's take a look at some of the similarity metrics. So Pearson correlation is something we are familiar with. So this is how you would compute the Pearson correlation, WIK, using the entries for the I and K, and or cosine similarity, which is the angle between these two vectors. So let's take a look at a specific problem here. We want to find, for given this matrix, we want to find this entry. So this entry is the fourth row and the second column. So essentially what we're trying to do is to find fourth row, second column. So according to the formula, it's going to be the average of the fourth row, which turns out to be 4. We just add these two, divide by 2, so we get 4 here. And then we find all the k's that are similar to this one. So for example, we find that this one is the most similar. In some ways, there's a distance of 1 between these two in this case. And so we find that vector here, matrix here. So this is the user k. We only found 1k. So in this case, our WIK would be 1. We used just the Euclidean distance between the two. And then we take the WIK is 1, then we take XKJ. SKJ is how the kth user, in this case this one, rated that item, so that we get 2 here. And then the average of that kth user, in this case the k is 2. The average of these two is 3.5. 5 plus 2 divided by 2, so we get 3.5. Divide by sum of the weights. So obviously we just had one weight, so that would be just 1. So we get the missing information here as 2.5. Note that we are using WIK as the absolute distance, but we didn't really use the Pearson correlation to do this. So if you do it a different way, you might come up with a different estimate here. But the goal is to really follow this formula and understand how to do that. All right. So that's sort of the conclude this lecture. And the item approach is perhaps the same thing. Okay, so let's do one more quiz and then we will wrap up this video. Suppose there are many users than items, so that means many users, so that means it's m is greater than or equal to n, highly greater than. Assume we use a regular matrix representation, not sparse matrices. Which of the following methods will be more efficient for predicting missing element? So in this case, the correct answer is the item approach will be more efficient because you will have more things to compare. But the user item may not be approached because here you notice that we are comparing columns and these columns are high dimensional vectors. So the correct answer should be 2. So this concludes the short video on collaborative filtering.